Hey, welcome to our introductory video on section 5.6, where we'll be talking about graphing rational functions. All right, so in the last couple videos, we introduced rational functions and then talked about their domain. In this video, we're going to talk about all the pieces we need to actually graph these functions. And fair warning, it's quite a bit. So on the next midterm or exam, when you have a note card, it's probably best to make sure you write down all the things you need for these graphs. So one, we want domain. Two, we'll want x-intercepts on our graphs. Three, y-intercepts. Four is end behavior. All right, so these four are all things that we're used to. We're used to making sure we know the domain, making sure we have the x-intercepts, the y-intercepts, the end behavior. Five is another one we're used to, where it's behavior between roots. Or actually, let's put that off for six, and you'll see why in a second. Five is asymptotes, which we'll define in a couple minutes for our video. And six is behavior between roots and asymptotes. So that's six different things that we need to make sure that we have for our graph. So for graphing rational functions, I usually find it best to just start with drawing a plot and then trying to knock off each of these one by one. I think that plot's actually a bit too small. And so currently these are ordered in a way so that way you don't need behavior about something in the future before you do something in the past. For instance, it's good to know what the domain is before trying to find x and y intercepts or anything else following it. It's the x and y intercepts are can go either way, but it'd be hard to find the end behavior before you know the x-intercepts, because we usually want to know what's going on beyond all the x-intercepts. And similarly, we can't find behavior between roots and asymptotes until we know the roots and the asymptotes. Whatever asymptotes is, we haven't defined them yet, but we'll get there. All right, so let's get our domain. I'm going to be a little bit fast. I'm going to say that it's our domain is r minus plus or minus 4. And it's your job to figure out how I got that domain. So take a second, pause the video and think about it, and review the last video if you're unsure. 2, our x-intercepts are still the same. It's just where f of x equals 0. And let's actually label what these are. That's domain. And this is going to be the x-intercepts. And so where the function equals 0, we're going to remember that we're looking at this fraction. And whenever we have 0 divided by something, we have 0. So all we have to do is look for where the top is 0. And so then we just do that and we can figure out that x equals 1 is our root. All right, so now we'll put these three things on. First, we have our root at 1, and then we have our asymptote. We have our domain where we can't have plus or minus 4. And so what we actually do is mark 4 and we draw a vertical dotted line through it. Do the same thing at -4. And this line is actually what we call an asymptote. All it means is that it's a place, a line on the graph where the function doesn't exist, and the function will get infinitely close to that dotted line, but never touch it. All right. We'll see what that looks like when we graph our function. Let's stick with green still for 3. We want our y-intercept. To get that, again, we just plug in, we just look at f of 0 the same way we always have, and we get -1 over -16, or 1/16. And we can mark that on our graph. Okay. The next thing is end behavior. And this is actually going to be different than what we've done before. So in previous videos, we've looked at what happens when we have polynomials and we're looking for end behavior. Now we're talking about what happens with these rational functions. So for this one, we have to think a little bit harder about end behavior. So we have this function, it's x minus 1 over x squared minus 16. Okay, so what happens for large x? So when we plug in really large positive values or really large negative values, so if we plug in x is 1,000,000, then we can kind of think about it as we have 1,000,000 divided by, so plug in f of 1,000,000 is approximately 1,000,000 over 1,000,000 squared. We ignore this 1 in the 16 for this guess, because 1,000,000 minus 1 is still pretty close to 1,000,000, and 1,000,000 squared minus 16 is still pretty close to 1,000,000 squared. You know, it's kind of like the same way that when you're talking about Jeff Bezos's wealth, you know, when you're talking in the hundreds of billions, you're not really concerned about like plus or minus $100. Like if he loses $100, you're not going to say that his net worth really changed. That's the same thing that's going on here. If you have 1,000,000 and you lose 1, you're still basically at 1,000,000. And so that we have 1,000,000 divided by 1,000,000 squared, and that's just 1 over 1,000,000. So it's pretty small. We can see that that's actually kind of happening if we plug in any other big numbers. If we change these to 1,000,000,000, we'd have 1 over 1,000,000,000, which is even closer to 0. So we actually get that the end behavior goes to 0. I guess we should write it as we always have. G of x goes to 0 as x goes to plus or minus infinity. Typically, this is tricky for students to master and understand. So it's good to do practice problems with it, try and reason out for yourself why this has to be true, or come to office hours for a deeper explanation of what's going on. And we'll talk about this in other examples and try and make sure everyone's comfortable. Okay, so now we know that the end behavior is headed to 0. We already have our asymptotes on there after finding the domain. And now we just have to find our behavior between the roots and the asymptotes. And once we get that, we'll actually be able to get our end behavior out pretty quickly. And actually, maybe we'll just start with our end behavior. Anyways, so what we'll do is first check to see if after 4, for numbers greater than 4, if we're positive or negative. So if we plug in f of 5, we get 4 over 25 minus 16. That's 4/9, which is a positive number. So the same way we discuss this with polynomials, we know that we're going to be positive and also approaching 0. So our graph looks something like this blue line, just headed to 0. And we know it can't cross to be negative, or else it would have another root, but we know it doesn't have another root. So then it starts to come to this line, and it actually shoots straight up, almost straight up. It's still a function, so it's not technically vertical, but for our purposes, it'll look kind of vertical. It gets infinitely close to this dotted line, but it never actually touches it. In our next example, we'll talk even more about this behavior. We would have to do a check for the behavior between 1 and -4, but we've already actually checked a point getting the y-intercept. So we know that our graph over here has to look something like this, going up. And now we want to know if this bounces or crosses. And it turns out that the same rule we had before applies. This has multiplicity 1. So it has that to the power of 1. And so because that's an odd power, that tells us that it's going to cross and go down. So something like that, where it approaches that asymptote again. And now we just need to look at what happens when we're less than -4. And so we can just plug in another value, like f of -5. And we'll get -6 over 25 minus 16, which is -6 over 9, -2/3. Regardless, the takeaway is that it's negative. So we're still negative on this other end. And so we get pushed along the asymptote there and trend out to 0 as we go far out to the far negatives. And that's what the graph of our function looks like. So these, as you can see, get kind of messy because there's a lot of moving parts going on. But we'll do a lot of problems, and it always breaks down to just finding these 6 features: the domain, the x-intercepts, the y-intercepts, the end behavior, the asymptotes, and the behavior between the roots and the asymptotes. All right, so we're going to stop here for this video. In our next video, we're going to talk about why asymptotes push the function up and down towards plus or minus infinity. All right, see you in the next video.